is chapter number 5 of Introductory Chemistry, Molecules and Compounds. By the end of this chapter, you will be able to restate the law of constant composition. Also, you will apply the law of constant composition with calculations. You will write chemical formulas. Also, you will be able to determine the total number of each type of atom in a chemical formula. You will be able to classify elements as atomic or molecular. Also, you'll be able to classify compounds as ionic or molecular. Another learning objective is that you will be able to write formulas for ionic compounds. Also, you will be able to distinguish between common and systematic names for compounds. You will name binary ionic compounds containing a metal that forms only one type of ion. Also, you will be able to name binary ionic compounds containing a metal that forms more than one type of ion. You will be able to name ionic compounds containing a polyatomic ion. Also name molecular compounds as well as binary acids. And you will be able to name oxyacid containing an oxyanion ending in ate and also in ite. And finally, you will be able to calculate formula mass. We have mentioned before that matter is composed of atoms, but that doesn't mean necessarily that the properties of matter are the same as the properties of the elements itself. So for example, we have sugars, but the property of sugars differ or are not the same as the property of carbon, hydrogen, or oxygens that are the elements that compose sugar. Ordinary table sugar is a compound called sucrose. A sucrose molecule, such as the one shown here, that is this one, okay, we can see that we have carbon, that is the black sphere, oxygen, and also hydrogen. So the sucrose, that is the table sugar, is composed by all those three atoms. Now, the property of sucrose are very different from those of carbon, shown here in the form of graphite and hydrogen and oxygen. Okay, so the properties of sucrose is totally different from the properties of carbon, hydrogen, and oxygen itself. The same happened with the salt. The properties of salts differs from those properties of sodium and chlorine, the two elements that compose salt. For example, elemental sodium is an extremely reactive metal that dulls almost instantly upon exposure to air. But on the other hand, the chlorine, that is the other element that composes the sodium chloride or table salt, is a yellow gas with a pungent odor. It is a highly reactive and poisonous. But when we combine these two elements, we can produce the sodium chloride, the table salt. The compound formed by sodium chloride is table salt, and the properties of a compound are in general different from the properties of the elements that compose. So sodium is not a gas, it also is not poison, it doesn't react with air, okay, and also has specific flavor different from the chlorine and also for the sodium. So this is an example of how properties of a compound is totally different from the properties of the element itself. Now, many natural substances are compounds. Some of the substances we encounter in an everyday life are elements, but most are not elements. They are compounds. Free atoms are very rare in nature. You can find a lot of atoms by itself, going all around the places. They are all basically combined to produce those compounds. A compound is different from a mixture of elements. In a compound, the elements combine in fixed definite proportions. Okay, so when we have a compound, for example, water, always you're going to have two hydrogens and one oxygen. Always. That's going to be the combination of those two elements to produce water. In a mixture, you can have any proportion whatsoever. You can have 10 hydrogens, 12 oxygens, 24 sodium. So that will be a mixture. But in a specific compound, even though you have a pound of that compound, or you have 1 kilogram, or you have 1,000 kilograms, the proportion between the elements that produce that compound is going to be always the same. H2O, for example, for water. A compounds or compounds display constant composition. Here we're going to have an example of a mixture. This balloon is filled with a mixture of hydrogen and oxygen gas. So here we have the oxygen, that is the red, and the hydrogen, that is the white. Here we have a mixture of both type of gas. The relative amounts of hydrogen and oxygen are variable. So there is no specific ratio. You can have more oxygen or more hydrogen. It all depends on the sample that you have. Now, in a chemical compound, is a little bit different, because you're going to have just one type of a compound in, for example, here in this balloon, and it's water. So you're going to have here H2O, and the ratio is going to be always 2 hydrogen, 2 atoms of hydrogen, and 1 atom of oxygen. Okay, so this one is a compound, and this one is a mixture. Okay, in a compound, you have a specific ratio between those elements, and in a mixture, you can have a relative. It's going to depend on the sample, so it's not like a specific ratio between those elements or compounds also. There is a law that is called the law of constant composition. This one was established best by Joseph Proust, and formally stated that the idea that the elements combine in fixed proportion to form compounds. This law basically states the following: all samples of a given compound have the same proportions of their constituent elements. So sodium chloride, for example, table salt, is going to be always sodium and chlorine. Um, Water always going to be H2O. Hydrochloric acid is going to be always HCl. Okay, so that's the proportion, 1 to 1 in the case of HCl, and 1 to 2 or 2 to 1 in the case of water, 2 hydrogen and 1 oxygen. So that's basically the law of constant composition. All samples of a given compound is going to have always the same proportion of their constituent elements. So the mass ratio of elements in water is basically constant. Here we have, if we have a sample of 18 grams, for example, of water, we will get always 60 grams of oxygen and 2 grams of hydrogen. Or a ratio between these two, a mass ratio between oxygen and hydrogen of 16 grams divided by 2 grams, 60 grams of oxygen divided by 2 grams of hydrogen is going to be equal to 8. Okay, this is basically the ratio. For every 8 grams of oxygen, we're going to have 1 gram of hydrogen. And that mass ratio is going to be always the same for pure water. Okay, it doesn't matter what origin is, what always for water, you can have a ratio of 8 grams of oxygen for each gram of hydrogen. Another example is using another compound that is called ammonia. And also the mass ratio for this compound is also constant. If we have a sample of ammonium of 17 grams of ammonia, we will have 14 grams of nitrogen and 3 grams of hydrogen. Okay, so for of all those 17 grams, 14 will be from nitrogen and 3 grams will be from hydrogen. Or also a ratio, mass ratio between nitrogen and hydrogen will be 14 grams of nitrogen divided by the 3 grams of hydrogen. This will be 4.7. So that means that for ammonia, you will have a mass ratio between nitrogen and hydrogen of 4.7 grams of nitrogen for each gram of hydrogen. Okay, even though atoms combine in whole numbers ratio to produce a compound, okay, you're going to have always um, whole numbers, okay, to produce the compound. Their mass ratios are not necessarily whole numbers, as this is example. Okay, the example we have a 4.7, so that's not a whole number, but it's okay because it's a ratio. But when we are talking about the number of atoms in a compound, those numbers are going to be always whole numbers. Okay, 1, 2, 3, 4, or whatever they need to produce that specific compound. So talking about compound, let's introduce the chemical formulas, how we can represent compounds. As we mentioned before, compounds have constant composition with respect to mass because they are composed of atoms in fixed ratios. A chemical formula indicates the elements present in a compound and the relative number of atoms of each. For example, as we have been mentioned in this chapter, water, H2O, is the chemical formula for water. It indicates that water consists of hydrogen and oxygen atoms in a 2-to-1 ratio. Okay, and this ratio is the ratio of atoms to produce this specific compound. 2 atoms of hydrogen for each atom of oxygen. This is not the mass ratio. Okay, this is just the ratio between the atoms that produce the specific compound. The formula contains the symbol of each element accompanied by a subscript indicating the number of atoms of that element. By convention, a subscript of 1 is omitted. So here we have the example of water. Here we have H2O. H is the symbol for hydrogen. 2, this subscript indicates that we need 2 hydrogen atoms. And here we have the O, capital O, and also capital H, that represent another element, that is the oxygen. This is the symbol for oxygen. And we have here, we don't have a 1, okay, because when we just need 1 atom, we imply that just by the symbol is just 1. Okay, so if you don't have a subscript, but you have the symbol of an element, that means that you have 1 of that element. So common chemical formulas include the following: sodium chloride, NaCl, for table salt, indicating sodium and chlorine atoms in a ratio of 1-to-1, 1 atom of sodium and 1 atom of chlorine. For carbon dioxide, we have here a ratio of 1-to-2 for 1 carbon atom and 2 atoms of oxygen, okay, to produce the carbon dioxide. That will be the ratio in the terms of atoms. For every atom of carbon, we're going to have 2 atoms of oxygen and carbon dioxide. For sucrose, the one that we introduced this chapter, we used to introduce the chapter, we have C12H22O11. That means that a molecule of sucrose, okay, have 12 carbons, 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. So the ratio will be 12, 22, and 11. That will be the ratio in the perspective of atoms. Okay, remember, this is not the mass ratio. This is just the ratio between atoms to produce a specific compound. So the subscript in a chemical formula represent the relative numbers of each type of atom in a chemical compound. They never change for a given compound. Okay, so always water is going to be H2O. H2O2 is not water. Okay, that's another compound. So if for any reason the subscripts are different, we have a different compound. Even though the elements are the same, but the ratio in H2O2 is from 2-to-2. In water is 2-to-1. So because we have a different ratio in the sense of atoms, we have a different compound. So changing a subscript makes a totally different compound. Here we have carbon monoxide. The subscript in a chemical formula are part of compound's definition. If they change, the formula no longer specifies the same compound. We will have a different compound. So carbon monoxide is the chemical, or CO, both capital, is the chemical formula for carbon monoxide, an air pollutant with adverse health effects on humans. Now, what happens if we change the subscript of the oxygen in CO from 1 to 2? Now we have a different formula, and because of that, we will produce a totally different compound. So now instead of CO, we will have CO2, and this one is carbon dioxide. And it's not that you have a different number of atoms or ratio, but always also the properties of this compound is totally different from the one before, from carbon monoxide. Carbon dioxide, for example, is relatively harmless. It's a product of combustion and human respiration. We breathe small amounts of it all the time with no harmful effects. So just because we have one more um, atom makes a totally different compound from the one before, not just in name, not just in aspect, but also in properties. Now, how to list the elements in order in compounds. The first rule basically is that chemical formulas list the most metallic elements first. So if we have sodium chloride, that is table salt, the sodium is from family number 1, while chlorine is from family number 7. Sodium is a metal, chlorine is a nonmetal, so that's why we write a sodium chloride as NaCl. We write first the most metallic element and then the other ones. In compounds that do not include a metal, the more metal-like element is listed first. Metals are found on the left side of the periodic table, as I mentioned before, and nonmetals on the upper right side. Among nonmetals, those that to the left in the periodic table are most or more metal-like than those to the right and are normally listed first. So we write, if we have an element of nitrogen and oxygen, we will write NO2 and NO. We're not gonna write O2N or ON, okay, because N is more has a more metal-like, okay, property than oxygen. So that's why we write first the nitrogen and then the oxygen. Within a single column in the periodic table, elements toward the bottom are more metal-like than elements toward the top. Okay, so the ones at the bottom in the same family, okay, or column, the single column, the ones at the bottom are more metal-like than the ones in the top. So that's why if we have a compound with a combination of atoms of sulfur and oxygen, we will write in the chemical formula first this sulfur and then the oxygen, not the oxygen and then the sulfur, because the sulfur is in the lower part, okay, of oxygen. Okay, it's lowered in the family of number 6. Okay, that is the family of oxygen. So that's why sulfur is you need to write sulfur first, because this one is more metal-like than oxygen. So the specific order for listing nonmetals elements in a chemical formula is basically here in this table: carbon, phosphorus, nitrogen, hydrogen, sulfur, iodine, bromine, chlorine, oxygen, and fluorine. And also there are a few historical exceptions in which the most metallic element is named first, such as hydroxide ions, okay, which is written as OH minus. This is a polyatomic ion, and it's called hydroxide ion. And you're gonna write first the most non-metal and then the most metal-like, okay, because hydrogen has a more metal-like properties than oxygen. But we when it's an ion, okay, this is when it's an ion, polyatomic ion, hydroxide. We're gonna write first the oxygen and then the hydrogen. This is a specific exception, okay, of the rule that we have seen in the last few slides. So how to represent compounds with polyatomic ions? Some chemical formulas contain groups of atoms that act as a unit. When several groups of the same kind are present, their formula is set off in parentheses with a subscript to indicate the number of that group. Many of these groups of atoms have a charge associated with them and are called polyatomic ions. As we mentioned before, OH is going to be a polyatomic ion because you have more than one atom to produce that ion. Most So far we have seen just ions with one element: sodium, sodium plus 1; chlorine, Cl minus 1, and those ions are just with one element, okay? But now we can have ion with more than one atom. as an example, we mentioned before in the slide before, OH, hydroxide ion. This is an example of a polyatomic ion. To determine the total number of each type of atom in a compound containing a group within parentheses, multiply the subscript outside the parentheses by the subscript for each atom inside the parentheses. Okay, so this is to determine the total number of each type of atom in a compound. And we're going to see an example in the next slide. So here we have um, we need to determine the number of each atoms in MgNO3 2, okay, magnesium nitrate. Here we have that magnesium nitrate indicates a compound containing one magnesium atom, as we can see here, Mg, okay, and two NO3 minus one ion. NO3 minus, okay, nitrate here, this is a polyatomic ion. Okay, it's an ion because we have a charge of 1 minus here, and polyatomic because we have more than one atom to produce this ion. We have here 4 atoms, 1 of nitrogen and 3 of oxygen. So if we need to determine the number of atoms for this molecule, okay, magnesium nitrate, we have 1 magnesium, and in nitrate we have NO3, so we have 1 nitrogen for each polyatomic ion. But because we have this 2 subscript here outside the parentheses, that means that we have 2 of this polyatomic ion. So we have 2 nitrogen. And for each nitrate, we have a 3 oxygen. But because we have 2 nitrate, that means that it's going to be 3 times 2, 6 oxygen. Okay, so here we have 1 magnesium, we have 2 nitrogen, and we have 6 oxygen. In other words here, another way to try to understand this, we have once again the magnesium nitrate here. There's the symbol for magnesium. We have there is no number, no subscript for magnesium, so that means that we have just one atom of magnesium. While in the right side, we have the polyatomic ion. Okay, this one is nitrate, and we can see here that we have 1 nitrogen, okay, because it's implied that we have 1 there, and 3 oxygen. And now this is inside the parentheses. In the outside of the parentheses, we have another subscript. This subscript affect all the things that are inside the parentheses. This 3 is going to affect just is going to show us the number of the element that is right before it. Okay, so we have 3 oxygen. Okay, 3 oxygen, we have 1 nitrogen, and we have 2 nitrates. So we have 2 polyatomic ions of nitrate. So that's why it means that we have for each, this is for each nitrate, 1 nitrogen and 3 oxygen. But because we have 2, it's going to be 2 times 1, 2 nitrogen, and 3 times 2 is going to be 6 oxygen. Now, there are different types of chemical formulas. One of them is known as the empirical formula. This one gives the relative number of atoms of each element in a compound. The other one is known as the molecular formula. This one gives the actual number of atoms of each element in a molecule of a compound. For example, the molecular formula for hydrogen peroxide is H2O2, but its empirical formula is HO. So as you can see here, both of them are multiple of 2, so you can divide this by 2, and you're going to have 1 and 1, and this represents HO is going to be the empirical formula for hydrogen peroxide, H2O2. Remember that the molecular formula is always a whole number multiple of the empirical formula. Okay, so it could be the same, or it could be a whole number multiple of that empirical formula. So in this case, H2O2 is the molecular formula, and the HO is the empirical formula. But we can have, and I think it's most of the cases of different molecular formula that also they are the empirical formula. For example, H2O. H2O is the molecular formula for water, but also is at the same time the empirical formula because you don't have any multiple that you have for 2 and for 1, okay, that are the same for them. So the third one is the structural formula. This one uses lines to represent chemical bonds and shows how the atoms in a molecule are connected to each other. So we have basically three different type of chemical formulas. The empirical formula, the ones that give us the relative number of atoms in a compound. The molecular formula that give us the actual ratio, okay, between the elements of a molecule in a molecule of a compound, and also the structural formula that this one gave us information about how the atoms are bound together. Okay, what is the sequence, the order of the atoms in a specific molecule. We have different types of chemical formula. The first one is known as the molecular models. The molecular models are the three-dimensional representations of molecules and is used to represent compounds. We use two types of molecular models. One is known as the ball and stick, and the other one is known as the space filling. In ball and stick models, we represent atoms as balls and chemical bonds as sticks. The balls and sticks are connected to represent the molecule's shape. The balls are color coded, as we can see here, okay? And we mentioned before, for example, the white is hydrogen, black is carbon, and red also is going to be oxygen. This type of blue, turquoise is going to be like nitrogen. Fluorine is a little bit like yellowish. Phosphorus is a more intense, like navy blue. Yellow is going to be sulfur, and the green one, most of the time, it represent the chlorine. In space filling models, atoms fill the space between each other to more closely represent our best idea for how a molecule might appear if we could scale it to a visible size. So we're going to have now an example. I'm going to show different models, okay, with that type of molecule. So this molecule is going to be methane. It's going to be CH4. So the molecular formula of methane indicates that methane has one carbon atom and four hydrogen atoms. So this is the molecular formula, the one that gives us the information about the ratio between the atoms that form a specific molecule or compound. This structural formula shows how the atoms are connected. Each hydrogen atom is bonded to the central carbon of atom. So we have here the central carbon atom, okay, and we have all the hydrogens surrounding that carbon, and in each of them we have four different types of carbon-hydrogen bonds. Okay, we have one here, one here, one here, one here, four bonds of carbon-hydrogen to produce the methane formula. And these are the two models, okay, the ball and stick models that we mentioned before in the slide before, as well as the space filling model. This illustrates the geometry of the molecule, how the atoms are arranged in that three dimensions. So here we have the carbon in the middle, and the four hydrogens around that carbon. This is the ball and stick, okay, model, and this one is a space filling model for methane. Now, images makes the connection between the world around us and the world of atoms and molecules. So the macroscopic world. The macroscopic world is what we can see. We see here a glass of water, okay? In the atomic and molecular world, we can see the particles, okay? So this one is basically the atomic or the molecular perspective, the molecular world. So we have here, we can see the molecules of water. The symbolic way that chemists represent the atomic and molecular world. So it's basically this one, okay? This one is the symbolic way that most of the time us as chemists represent different type of molecules. Now let's have a molecular view of elements and compounds. Pure substances may be either elements or compounds. Okay, pure substances could be just elements, okay, or it could be compounds. Elements may be either atomic or molecular. Remember, atomic is that it just has one atom, okay, not one type, just one atom. And molecular is that it has more than one atom. It could be both the same or both different. Okay, so for example, elements, in this case, in elements, we're gonna have both needs to be the same. So for the most of the metals, it's gonna be just one atom. So if we're talking about gold, is Au. We're gonna talk about platinum, is gonna be Pt. Now, if we're gonna talk an element for example, oxygen, is going to be O2, and that's a molecule. Even though we have two atoms, okay, of oxygen, but um, the combination of those atoms of oxygen will produce the element of oxygen that is molecular, O2, because we have more than one atom. When we have just one atom, we're going to have an element that is atomic, and we're going to have, when we have two atoms of the same element, we're going to have an element that is a molecular. Now, compounds may be either molecular or ionic. Okay, so we can have compounds when when the atoms of or elements of that compounds are all non-metal, is known as a molecular compound. When we have one metal as part of the chemical formula, now that compound is an ionic compound. So let's talk about the classification of elements and compounds. So pure substances, as we mentioned before, could be elements or compounds. The elements could be atomic, for example, neon, okay, and also could be molecular, for example, O2. So these two are elements, but this one is an atomic element, and this one is a molecular element. The atomic element was going to have just one atom, and in the molecular element, we're going to have two atoms. The same way with chlorine is Cl2, iodine I2. Okay, then those are elements with in a molecular perspective or as molecule. When we have compounds, we mentioned that we have two types of compounds. One of them is the molecular one. And the molecular one, we have here an example of H2O. Okay, and we can have also ionic compounds, as we can see here, the sodium chloride, and you can see that sodium is a metal. Okay, so that's why when you have a metal as part of the chemical formula, those compounds are going to be classified as an ionic compound. So elements may be atomic or molecular. Atomic elements are those that exist in nature with single atoms as their basic units. Most elements fall into this category. Okay. Now, the molecular elements do not normally exist in nature with single atoms as their basic units. Instead, these elements exist as diatomic molecules, two atoms of that element bonded together as their basic unit. So, an example of this is mercury. Mercury is an example of an atomic element. An atomic element and a metal are single mercury atoms. Okay, we can see here that they are just one type of atom, mercury. Okay, and this is how you can find mercury in nature. The basic units that compose mercury, an atomic element, and a metal are single mercury atoms. Another way, in a molecular element, the basic units that compose chlorine, a molecular element, are diatomic chlorine molecules, each composed of two chlorine atoms. So here we have an example of an atomic element, that is, the basic units is atoms of mercury, okay? And here we have an example of molecular elements where the basic units are diatomic chlorine molecules. So here we're going to have a list of the most common elements that exist as diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, so these are basically the elements that exist as diatomic molecules in nature. Now let's talk now about the compounds. We have been talking about the elements. Now let's talk about the compound. We can have two different classification: the molecular one or the ionic. Molecular compounds are compounds formed from two or more non-metals. The basic units of molecular compounds are molecules composed of the constituent atoms. The ionic compounds contain one or more cations paired with one or more anions. Okay, and this is due to the ability that the metals have to produce the cations or the positive ions or ions with positive charges. So whenever we see a metal, we're going to classify that compound as an ionic compound. And when all of the atoms are nonmetals, we can classify them as the molecular compounds. In most cases, the cations are metals and the anions are nonmetals. Compounds may be molecular or ionic. The basic units that compose dry ice and molecular compounds are CO2 molecules. Okay, so when we're talking about molecular compounds, we talk about molecules. Okay, the basic units are molecules. When we talk about the ionic compound, the basic units that compose table salts and ionic compounds are sodium chlorine formula units. Okay, so in the case of a molecular compound, the basic unit is molecule. In the case of ionic compounds, the basic units are the formula units. Now let's talk a little bit about the ionic compounds. When a metal which has a tendency to lose electrons combines with a nonmetal which has a tendency to gain electrons, one or more electrons transfer from the metal to the nonmetal, creating a positive and negative ions that are attracted to each other. So as you can see here, in an ionic compound, there is an electrons transfer. Okay, there has been electron that has been transferred from the metal, and because that metal lose that electron, now we have a positive charge. That's why most of the metals can create cations, while the nonmetal has the ability to receive that electron was released by that metal, and because of that, the nonmetal would turn out it was neutral, but now because it received this electron, it's going to be a negative charged particle known as an ion. A compound composed of a metal and a nonmetal is considered ionic. The basic unit of an ionic compound is the formula unit, as we mentioned before. And unlike molecular compounds, ionic compounds do not contain individual molecules, but rather the cations and anions in an alternating three-dimensional array. Okay, so that's the basic unit. That's is basically that arranged between ions. Okay, to produce that crystal lattice of that specific compound. Now, how can we write formulas for ionic compounds? First of all, review the elements that forms ions with a predictable charge. Ionic compounds always contain positive and negative ions. Always. That's why they are called ionic compounds. If the chemical formula, in the chemical formula, the sum of the charges of the positive ions that are known as cations must always equal the sum of the charges of the negative ions known as anions. So, here are some rules that you can follow to write this ionic compounds formula. Write the symbol for the metal and its charge followed by the symbol of the nonmetal and its charge. Number 2, make the magnitude of the charge on each ion without the sign become the subscript for the other ion. If possible, reduce the subscript to give a ratio with the smallest whole numbers. And check to make sure that the sum of the charges of cations exactly cancels the sum of the charges of the anions. So let's do an example. Write formulas for ionic compounds that form from aluminum and oxygen and magnesium and oxygen. So Aluminum has a charge of +3, and oxygen has a charge of 2 minus, okay, -2. So we're gonna switch those the magnitude of the charges, okay, and they're gonna become the subscript of the other element. So aluminum is +3, so this 3 is gonna be the subscript now of the oxygen. Well, we're gonna have oxygen -2, and this 2, the magnitude of the charge, is gonna become the subscript for aluminum. So the chemical formula for aluminum oxide is going to be Al2O3. Between magnesium and oxygen, okay, magnesium is +2. Remember that magnesium is a family 2, and oxygen is going to be -2. So here we can see that we can do this in two ways. When we have the same magnitude, we're going to need just one and one of each of them. So it's going to be MgO. Or you can switch the magnitude and you're going to have Mg2O2, but both of them have a multiple, that is multiple of 2. We can divide by 2, and eventually we're going to have MgO, that is the molecular formula for magnesium oxide, okay? So it's MgO2. So we need to divide here by 2 to have that specific ratio, okay, between MgO. So writing formulas for compounds with polyatomic ions. Recognize the polyatomic ions in a chemical formula by becoming familiar with these common polyatomic ions. We're going to have here a table with different polyatomic ions that we're going to use during this semester and also the next course. So some common polyatomic ion: acetate, okay, carbonate, nitrate, nitrite, chromate, perchlorate, sulfite. The important thing here that you need to understand is that the combination of all these atoms, okay, produce a charge, or it has a charge of -1 in the case of the nitrite, okay. Sulfate is going to be SO4 -2. Hydrogen phosphate is going to be HPO4 -2. So for each hydrogen phosphate that you're going to use, you're going to have a charge of -2. So if you need 3 hydrogen phosphate, that means that you're going to have a charge of -6, okay, because each of them has a -2 charge. And if you, for any reason, need 3 of them for create a specific molecule, you're going to have a -6, okay. That will be basically the charge due to this polyatomic ion, okay. So don't think about to separate this by magnesium and the charge of oxygen -2, and no, 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 no. This is just the charge -1 is the charge of the whole polyatomic ion of permanganate, okay, as well as SO3 is going to be -2. For O2 peroxide is going to be -2 always, okay. So that's the way that you need to understand this. Each polyatomic ion has a specific charge. It could be -1, it could be -2, it could be also +1. Ammonium basically is the only polyatomic ion with a positive charge. Okay, the ion of ammonium, NH4. Now let's talk about the nomenclature for compounds. Chemists have developed systematic ways to name compounds. If you learn the naming rules, you can examine a compound's formula and determine its name and vice versa. Many compounds also have a common name. H2O has a common name of water, but the systematic name is dihydrogen monoxide. Since water is such a familiar compound, everyone uses its common name, water, and not its systematic name. Common names can be learned only through familiarity, and there is no a system, okay, or rules to establish a common name. Naming ionic compounds. The first step in naming an ionic compound is identifying it as one. And we mentioned before that if we have a metal in a compound, that compound is classified as an ionic. So anytime you have a metal and one or more nonmetal together in a chemical formula, you can assume that compound is an ionic compound. So we can have two types of ionic compounds. Remember, the ionic compounds is the combination of an ion from a metal and an ion from a nonmetal element. So we can have an ionic compound from metals that forms only one type of ion. These are, for example, the metals that are in family 1. They are going to create cations with a positive 1 charge. That's the same way with the family number 2. Okay, from the metals of family number 2, they're going to be always they're going to produce always cation with a charge of +2. But in the transition metals, we can create cations, different cations from the same element. We can have a metal that can produce two different ions because, or cation. One is going to have a specific charge and the other one another. We can have a metal with a +2 and a metal with a +1 from the same element. Okay, so we can have two different type of ionic compounds, one from metals that forms only one type of ion, and another kind of ionic compounds with metals that could form more than one type of ions. So the first type is called the type 1 that contains a metal with an invariant charge, one that does not vary from one compound to another. The second type of ionic compound is called type 2 and contains a metal with a charge that can differ in different compounds. Such metals are usually but not always found in the transition metals section of the periodic table. Some transition metals, such as zinc and silver, form cations with the same charge in all of their compounds. So you're going to see always zinc with a 2 plus, and silver always going to be with a +1. Some may group metals, such as lead and tin, form more than one type of cation. Here we have a table with those metals that produce ions with invariant charge. Lithium is going to be always is going to produce always a cation of lithium +1. Barium is always going to produce an ion of barium +2. Zinc +2. This is always going to be the charge for zinc. You're going to see a different charge or ionic charge, okay, for zinc. It's going to be always +2. For potassium, the same thing. Always going to be +1. Now here you're going to have a table of metals that can produce ions with different charges. Chromium, for example, could produce a chromium +2 or chromium +3. Iron could produce iron +2 or iron +3. The same thing with tin. Tin could produce tin +2 or tin +4. And we have here different names that we're going to talk a little bit later about how to name this type of ions for the metals of or ionic compounds from metals type 2. So binary ionic compounds with metals of invariant charge. Binary compounds are those that contain only two different elements, okay? The names for binary ionic compounds contain a metal that forms only one type of ion have the following form: the name of the cation or the name of the metal itself, and the base name of an ion with the end of IDE. So you need to add the name of the anion and the end IDE, and that will be the whole number of the binary ionic compound. So since the charge of the metal is always the same for this type of compounds, it not need to be specified in the compound's name. So for example, the name of NaCl consists of the name of the cation, that is sodium, followed by the base name of the anion, that is chlor, because this is from chlorine, but with the end of IDE. So that's why the name is sodium chloride. So we use the name of the metal, okay, for the cation, and we use the base name of the element that produced the anion, and we add the ending IDE. So we have here sodium chloride, NaCl. So these are basically some common names of anions. So it's fluoride, comes from fluorine, but the end IDE, this is going to be when they are anions, okay? Chloride, bromide, iodide, oxide, sulfide, nitride. Okay, these are basically the anion names of those anions. So what about when the ionic compounds have metals whose charge may vary? Since the charge of metal cation in this type of compound is not always the same, the charge must be specified in the metal's name. We specify the charge with a Roman numeral in parentheses following the name of the metal. So, for example, we distinguish between copper 1 plus and copper plus 2 or 2 plus by writing a 1 Roman, this is the Roman number, to indicate the 1 plus ion, or the 2 Roman to indicate the 2 plus ion. So copper 1 or copper 2. And this is the way that we use to identify which of the at least two possible cations that could be formed for the same metal is the one that we are using. Okay, is the one that we need to create or find out the name. The full names for these types of compounds have the following form. The name of the cation, okay, it's going to be the name of the metal itself with, okay, the charge of the cation in Roman numerals in parentheses, and then the base name of the anion using the same ending as we used before, the IDE. So we have here an example. We can determine the charge of the metal from the chemical formula of the compound. The sum of all charges must be zero. Remember, when you have a compound, that compound is neutral. So that means that the charges must be canceled between the ions that form that ionic compound. Okay, so if you have a plus 4, you need a minus 4. If you have a minus 3, you need a plus 3. Okay, to cancel them when you are creating or looking for the molecular formula or chemical formula of an ionic compound. So the charge of iron in FlCl3 must be plus 3. Charge of the iron, okay, because chlorine is minus 1, and we have 3 of them. And because we have 3 of them, we have here a minus 3 charge because we have 3 Cls minus. So that's why the iron must be plus 3. So in that way, they can cancel the charge of this plus 3 iron can cancel the 3 charges of the chlorine, of the minus 1. And that way will be neutral. So the name for the compound FeCl3 is the name of the cation, iron, followed by the specific charge of the cation in parentheses, that will be 3, followed by the base name of the anion, that is chlor, for chlorine, but ending in IDE. So that means that we have here iron 3 chloride. That's the name of this compound, iron 3 chloride. Now let's try to name some ionic compounds that contains polyatomic ions. Some ionic compounds contain polyatomic ions, ions that are themselves composed of a group of atoms with an overall charge, as we discussed previously. Ionic compounds containing polyatomic ions are named using the same procedure we apply to other ionic compounds, except that we use the name of the polyatomic ion whenever it occurs. So we're going to see a few samples in the next slide. The first one, we have KNO3. K here is the metal. Okay, so that means that all of this, NO3, is the polyatomic anion. So we have the cation, that is potassium, and the polyatomic anion, that is nitrate. This is the name of this polyatomic ion. So that means that we have potassium nitrate. That's the name of this ionic compound with polyatomic ion. Another one is Fe, iron, OH, hydroxide. We saw this before. OH minus is hydroxide. And we have here OH minus 1, so we have 2. So that means that we have 2 negative charge due to the presence of hydroxide. So because we have a minus 2 here, okay, now the iron must be a plus 2. So in that way, can cancel the minus 2 from the hydroxides. So that means that we have iron 2, and this is hydroxide. So that means that the name is iron 2 hydroxide. If the polyatomic contains both a polyatomic cation and a polyatomic anion, we use the names of both polyatomic ions. So if we have something like this, NH4 is ammonium and NO3 is nitrate, so the name is ammonium nitrate. Now, let's name ionic compounds that contains oxyanions. Many polyatomic ions are oxyanions, anions containing oxygen. When a series of oxyanions contains different numbers of oxygen atoms, they are named systematically according to the number of oxygen atoms in the ion. So for example, if there are 2 ions in the series, then one with more oxygen atoms is given the ending ATE, and the one with the fewer is given the ending ITE, ate and ite. Okay, so that means that we have here nitrate is the one that has, here we have an oxyanion. We can see here that we have 1 nitrogen and 3 oxygen, 1 nitrogen and 2 oxygen. So this one has a higher number of oxygen. So we're going to use the ATE ending. So it's nitrate. And here we're going to use the ITE. So it's nitrite. Okay, for this one. This is nitrate and this is nitrite. The same thing happened with sulfur with oxygen. We have SO4, SO3. So because of that, sorry about that, we're going to have, this one has a larger number of oxygen, so it's going to be sulfate, the ending ATE. This one has a lower number of oxygen, is sulfite. Okay, so we have sulfate and sulfite. So the one, when we have oxyanions, the one with the larger number of oxygen is going to have the ending ATE, and the one with the fewer number of oxygen is going to have the ending of ITE, nitrate, nitrite, sulfate, sulfite. There's another type of ionic compounds that contains not just oxyanions, but also halogens. Okay, so if there are more than 2 ions in the series, then the prefix hypo means less than, and per meaning more than are used. So that means, for example, here we have ClO2 and ClO3. ClO2 has a lower number of oxygen than this one, so that's why I use the ITE, and this one is the ATE. So this is chloride and this is chlorate. But we have also another one that has a lower number of oxygen. So for that one, you use the and then hypo. So it's hypochlorite. And we also have another one with a larger number of oxygen. So we're going to use perchlorate. Okay, we use the beginning of per, okay, the prefix per, perchlorate, and here we're going to use the prefix of hypochlorite. So hypochlorite, chlorite, chlorate, and perchlorate. The same thing here with the oxygen and bromine. We have the bromite and bromate. Bromite is the one that has a lower number of oxygen between these two, and this one that has a larger number of oxygen. But we have another halo-oxyanion with a lower number of oxygen. So BRO minus is called hypo, the same thing, the prefix that means a less than, hyperbromite, the bromate, and because this one has a higher number of oxygen, it's called the perbromate. So when naming these ions in the homework, be sure to include the word ion in your answer, as in perchlorate ion, if we ask for write the name of those ions. So it's going to be chloride ion, bromide ion, periodate ion. Okay. So, polyatomic ions, we are exposed to them on a daily basis. The active ingredient in household bleach is sodium hypochlorite, which acts to destroy color causing molecules and kill bacteria. Baking soda contains sodium bicarbonate or sodium hydrogen carbonate, which act as a source of carbon dioxide gas in baking. Calcium carbonate is the active ingredient in antacids such as Toms and alkamints, and it neutralizes the stomach acids. And sodium nitrite is another example of polyatomic that we are exposed to them on a daily basis. Is a food additive used to preserve packaged meats such as ham, hot dogs, and bologna. Sodium nitrite inhibits the growth of bacteria, especially those that cause botulism. So that's why some of these polyatomic ions are really important because we are on a daily basis being exposed to them. Now let's talk about the nomenclature of molecular compounds. The first step in naming a molecular compound is identifying it as one. Remember, nearly all molecular compounds form from two or more nonmetal. If we don't have a metal in the atoms that form that molecule, that or compound, that compound is a molecular compound. We learn how to name binary two elements molecular compounds. Their name have the following form: prefix, name of first element, another prefix, and the name of the second element with the ending IDE. So as different as in the ionic compound, in the ionic compound we don't use prefixes, okay, for the names. We use prefixes for the oxyanions, that is different, okay? But for naming the compound itself, we don't use prefixes for the ionic compound. For the molecular compound, we need to use prefixes if we need to use them, not just in one of them. We need to use in both. Okay, so we're going to see an example in a few seconds. So when writing the name of a molecular compound, as when writing the formula, the first element is the more metal-like one. Okay, so that's basically the rule. So here the prefixes given to each element indicate the number of atoms present in that specific compound. Okay, so the prefixes that we're going to use are going to represent the number of atoms for that compound. These are some examples of the prefixes: mono, that represent one; di, dichloride, that is that is two; tri, that is three; tetra, that is four; penta, that is five; hexa, hepta, octa, nona, and deca. So these are basically the prefixes that we're going to use in this course for naming the molecular compounds. Exception to note when naming molecular compounds: if there is only one atom of the first element, the prefix mono is normally omitted. Okay, we don't use that much the prefix mono. So we have CO2 instead of monocarbon, it's just carbon. And D, because we have two, ox for the oxygen, and IDE, the ending. So that's why it's carbon dioxide, the name of this molecule. We don't use the mono because basically it's just one, so that we assume that we have just one of them. Now, the compound N2O, also called the laughing gas, is named according to the first element, nitrogen, with the prefix D, dinitrogen, followed by the base name of the second element, ox, prefixed by mono and the suffix IDE. So since mono ends with a vowel and oxide begins with a vowel, an O is dropped and the two are combined as monoxide. So the entire name is dinitrogen monoxide. That will be the name of N2O. We have two nitrogen and one oxygen. When the prefix ends with a vowel and the base name starts with a vowel, the first vowel is sometimes dropped. Vowel is dropped in monoxide but not in dioxide nor or in triiodide. Another type of molecular compounds are acids. They are also molecular compounds. The first step to name acid is to identify it as one. Acids are molecular compounds that form ions when dissolved in water. They are composed of hydrogen, usually written first in their formula, and one or more nonmetals written second. So whenever you have start or you see a compound with an H in the front, starting with an H, you can assume that that compound is an acid. Okay, for now, we can categorize acids into two groups: the binary acids, those containing only hydrogen and a nonmetal, and the oxyacids, those containing hydrogen, a nonmetal, sorry, and oxygen. So, acid formula has H as the first element, as I mentioned before. Okay, we have binary acid that contains only two elements, or we can have the oxyacids that contain oxygen, also have two elements and also oxygen. So binary acid is composed of hydrogen and a nonmetal. The name of the binary acids have the following form: hydro, the base name of the nonmetal with the ending IC, and you're going to finish the name by adding the word acid. So HCl is hydro. You start with the word hydro. Chloric, we have chlorine, but we're going to use the IC ending. And then we're going to add the word acid, hydrochloric acid. For HBr, this is bromine. So it's going to be hydro, we're starting with an H again. Hydrobromic, we're going to use the IC ending. And acids as the last word for this binary acid. So HCl here as a gas refers to hydrogen chloride molecule in the gas phase and not to the acid. Okay, so this one is not basically hydrochloric acid. So let's try this one. The name for H2S. The base name of S is sulfur, so the name is hydrosulfuric acid. Okay, hydrogen, hydrosulfuric with the sulfur and the ending IC acid. So we have there hydrosulfuric acid. Now we have also oxyacids. Okay, this one are acid that contains oxyanions found in the table of the polyatomic ions that we saw before. HNO3 contains a nitrate ion. H2SO3 contains the sulfite ion. And H2SO4 contains the sulfate ion. These acids are a combination of one or more hydrogen ions with an oxyanion. The number of H positive ions depends on the charge of the oxyanion, so that the formula is always charge neutral. So as you can see here, nitrate as an ion has a -1 charge. So that's why you need to combine the nitrate with one hydrogen to produce HNO3. You have here sulfite. Sulfite has a charge of -2. So that's why when it's an acid, this oxyacid is H2SO4. Okay, the combination of two uh, protons or two hydrogen plus one ion, okay, that can cancel this two negative charge of the polyatomic ion. Remember that every polyatomic ion has a specific charge. Sulfite is going to be always -2. Sulfate is going to be always also -2. The difference between these two are the number of oxygen, and that's why the ones that has the lower number of oxygen is the ending ITE, while the one that has a higher number of oxygen is the ATE. Okay, that's why sulfide and sulfate. And the sulfate also has a -2 charge, so that's why you need to combine this polyatomic ion with two hydrogens. So in that way, you have two positive charge from the hydrogen plus the two negative charge of one polyatomic ions of sulfate that will cancel, and you will have H2SO4. And this is a neutral um, molecule, okay, or compound. So let's see the following flow chart. We have oxyacids containing oxygen. We're going to use the IT, okay, naming of the oxyanion ends in ITE, and also the ones that use the ATE, the IT and 8. The names of acid containing oxyanions ending with ITE will take this form. We're going to use the OUS ending. Okay, we're going to use the base name of oxyanion with the OUS ending. And then we're going to use the word acid, the name of acids containing oxyanions ending with ATE. Now we're going to use the ending of IC, and also we're going to add the word acid. So if the oxyanion ends with ITE as an acid, now we're going to use the ending OUS with the base name of the oxyanion. If the oxyanion ends with ATE, now we're going to use the base name of the oxyanion, but the ending of IC, and to both of them we need to add the word acid because now we're talking about acid from oxyanions. So here we have some examples. We have HNO2 and HNO3. NO2 is nitrite, NO3 is nitrate. But when they are acids, okay, now the ITE use the ending OUS, so it's nitrose acid. And with the one that use or come from the ATE, the nitrate, is going to use the ending IC, so it's nitric acid. The same thing with H2SO4 and H2SO3. The SO3 as an oxyanion is sulfite. The SO4 is sulfate. But when we're going to use this base name, okay, to name the acid, now we're going to use sulfurous acid as the SO3. And IC, we're going to use the ic ending for the one that comes from the 8. So it's sulfuric acid. And also the same thing with the other examples. So here, basically, we have a huge flow chart to try to summarize the nomenclature of the different compounds. So if we have an ionic molecule, okay, remember that is the combination of a metal and a metal, we can have two possibilities. One that comes from, or one that is the metals that are forms, or the metal that can form just one type of ion, or we can have another type of ionic compound that is with the metal that can form more than one type of ion. For the ones that form just one type of ion, the naming is pretty simple. Just the name of the cation, that is the name of the metal, or the name of the element, and also the base name of the anion using that ending IDE. Okay, the name of the anion, that is a nonmetal. So you can use the ending of IDE. Here, calcium iodide. Okay, calcium is the cation from calcium, and the iodide from iodine, but we're going to use the ending IDE when we're going to name an ion, okay? When we have the cation that comes from a metal that can produce more than one cation, we need to use, okay, the Roman numeral to represent the charge of the cation. The same thing, we're going to use the name of the cation, that is the name of the metal. Sorry about that. And in parentheses, we're going to add here the Roman number that represent the charge of the cation. And then we're going to use the same base name of the anion using the IDE ending. Okay, so for example, FeCl3 is going to be iron. This iron is going to be +3 because we have 3 chlorine. And each chlorine, the charge of each one is -1. So because of that, we have 3 chlorines. So that means that we have a -3 charge. So to cancel that -3 charge with just one iron, that iron must be +3. So because of that is iron 3. And chlorine, we're going to use the ending IDE, so it's iron 3 chloride. For the molecular compounds, that these are just nonmetals, atoms, okay, that combine together to produce a molecular compound, we're going to use prefixes to both, okay, for the first element. And remember that the first element is the most like metal one, okay? So we're going to use a prefix that it could be mono, D, or three, or tetra, or penta, and the name of the first element. And then for the other one, if we need to use a prefix, we use a prefix and base name of the second element with the IDE. Remember that this one is the has the less uh, metal-like characteristic of both of them. So here we have P2O5. So that means that we have two phosphorus and we have five oxygen. So it's diphosphorus, okay? And the oxygen, this one we're going to use the ending IDE, is 5 pentaoxide. Ox from the oxygen and IDE from the ending of the rule, okay, for the molecular compounds. And finally, we have another group of compounds that are the acids. The acid, most of the time, are going to start with a hydrogen. It could be one or more than one hydrogen, but it's going to start with hydrogen and one or more nonmetals. Okay, so we can have binary acids or oxy acid. The binary acids are the ones that are just of two elements, the combination of two elements, hydrogen and another nonmetal. Okay, and the name is start with hydro, then the base name of the nonmetal, different from hydrogen, and using the ending IC, and you're going to add the word acid. So we have HCl is hydrochlor from chlorine, chlorhydric. Okay, hydrochloric, sorry, acid. Okay, so hydrochloric acid. That's the name of HCl. The other categorize of acid is the oxide acids. This one contains oxygen, and we're gonna use the if the oxyanion has the ending ITE, then you're gonna use the base name of the oxyanion with that ending OUS. And for example, H2SO3, SO3 is sulfite. Okay, so this one is gonna be the ending of sulfite. We're gonna remove the ITE and we're gonna substitute with OUS. So we're gonna have sulfurous acid. Okay, so for this one. If the oxyanion has the ending of ATE, then we're going to remove the ATE and we're going to add the IC ending and also the word acid for both of them. So here we have H3PO4. This will be phosphoric, okay, phosphoric acid because this comes from phosphate. But now as an acid, the ending is going to be basically phosphoric acid. So here we have another type of example, okay, SOCO is a molecular compound. So this is carbon monoxide. We have just one oxygen. This one is anionic because calcium is a metal. So, and calcium has just one type of ion because calcium is from family 2. And as I mentioned before, the family 2 always going to have a +2 charge, okay? So in this case, we're going to have, the name is going to be calcium fluoride. Here we have HF. HF is a binary acid because we have two type of atoms. And we're going to start with hydro, okay, with H, fluor, and then IC. So it's going to be hydrofluoric, and we're going to add the word acid at the end. Here we have an ionic compound. This is not an acid because it doesn't start with an H. So we can classify it as an ionic or a molecular. It's not a molecular because we have a metal. So because we have a metal, this compound is an ionic compound. And iron also have more than one type of ion. So that's why we need to use the Roman numbers. The nitrate here, okay, has a plus a -1 charge. We have 3. So the nitrate is going to give -3 charges. So the iron must be a +3. So that's why it's going to be iron 3 and nitrate. Then here we have an acid. Okay, so we start basically, here we have also the ClO4. This is an oxide acid. Okay, this one is chlorate. Okay, so we're going to use, instead of ATE, we're going to use IC. So this is perchlorate, is perchloric acid. Okay, because As an oxyanion, it's going to be perchlorate, but as an acid, it's going to be perchloric acid. And the same thing here. We have here a sulfite, okay, SO3. So we're going to remove the ITE ending, and we're going to use OUS, sulfurous in this acid, because we have an acid here. We start with H, okay? So in that way, it's basically a simple way to try to visualize the different option of nomenclatures. So finally, we're going to talk about the formula mass. The formula mass is basically the sum of the atomic masses of all the atoms in its chemical formula. So we have here the number of atoms of the first element, okay, in the chemical formula times the atomic mass of that first element. Then we're going to add the product of the number of atoms of the second element in the chemical formula times the atomic mass of that second element. And we're going to add all the ones that are necessarily dependent on each of the compounds, okay? So chapter 5, in review, we have different chemical principles. Compounds display constant composition. The elements that compose a particular compound are fixed definite proportions in all samples of the compound. We have chemical formulas that indicate the elements present in the compound and the relative number of atoms of each. These formulas represent the basic units that compose a compound. And also we talk about the chemical nomenclature. The names of simple ionic compounds, molecular compounds, and acids can all be written by examining their chemical formula. And also we talk a little bit about the formula mass of a compound, that is the sum of the atomic masses of all the atoms in the chemical formula for the compound. And this will be the end of chapter 5, Molecules and Compounds.